First, I would like to recall that the slope of the tangent line to the curve y equals fx at x equals c, which is also the instantaneous rate of change of the function with respect to x at x equals c, is given by the derivative of the function at c. Also, we can write it as f prime c, and it is the limit of f of c plus h minus f of c over h when h approaches 0. And this was the picture, and we realize that here is the sequence line between BFB and CFB, and as we are approaching the values of the x equals b to x equals c, we are really getting that this is a very good approximation for the real slope of the tangent line. We would like to use this to find the derivative of the function f(x) equals 4x to the power of 2 and x equals 3. So here's the template, so we're going to put this in the template. So it is limit of h approaches 0 of f of 3 plus h minus f of 3 over h. Now let's see, what is this one? So f of 3 plus h is the function f, which is 4x to the power of 2, but instead of x, we have to write 3 plus h. So this is in parentheses, because if you replace x by 3 plus h, then x to the power of 2 is 3 plus h in parentheses to the power of 2. F of 3 is just the value of the function when x equals 3. So let's substitute this, and we get that. Now we have to do some algebra. First, I'm going to expand the 3 plus h to the power of 2. Now we will multiply everything out, we will distribute the 4, and we get that. And now it's the fun part of cancellation. We can cancel that one, and we get that. Now we realize that if we would like to take the limit when h approaches 0, we have to cancel the h, but this is not a biggie because we can distribute h in the numerator, and we get that. So now we can cancel out the h's, and we get that this is just the limit of h approaches to 0 of 24 plus 4 times h. And when we substitute h equals 0, we get 24. So what is 24? It is the slope of the tangent line to the curve y equals 4x to the power of 2 and x equals 3. F prime c is a number when c is a number, because again, it is the slope of the tangent line. So it's a bit more interesting to find the derivative of the function, which is not just a number. So here is the definition of the derivative of the function f, which we denote by f prime x. It is the limit of f of x plus h minus f of x over h when h approaches 0, if obviously exists infinite. So if you see, this is going to be a function of x. Let's see now what is the connection between those two definitions. So we also realize that here we're getting a function, because the limit is with respect to h, not f. And here we get a number when c is a number. And here's the connection. If you take this function and you substitute x equals c, you will get f prime of c. It means that we can evaluate f prime of c when c is a number directly or by substituting in the derivative of the function fx. So before we will practice this, we would like to notice and see the notations for the derivatives, because it can be really confusing. So first of all, if y equals f prime, that f prime x is also y prime. And df dx is also dy dx. We don't say dy over dx, we say dy dx. And the same here, we say d dx of f, d dx of y. So we have actually two types of notations. The first two are using the prime notation, and the other ones are using what we call the Leibniz notation for derivatives. If you see, all of those are ratios. We will talk about this much later when we will learn about differentials. Example, fx equals x to the power of 2 minus x. So here are the different ways to express the derivative of this function. First I was using the prime notation, then I was using the Leibniz notation. Example, let's find the derivative of the function fx equals 4x to the power of 2 at x equals 3. But now we're going to use the fact that the derivative of the function at x equals 3 is f prime of 3. So now I'm going to differentiate the function itself. So let's start by finding f prime of x. This is the limit of fx plus h minus fx over h when h approaches 0. Always the difficult part is the yellow part here. What is f of x plus h? You just have again to be very picky about not forgetting parentheses. X is replaced by x plus h, so it should be bundled together in parentheses. F of x is just the function itself. So you would like to write it nicely, and now we are going to do the algebra. We will start by expanding the x plus h to the power of 2. Now we are going to distribute the 4. And now we have to notice all cancellations. And I see 1 here. And I get that. Now we'll have to distribute h in the numerator. So I can cancel it out. And get that. Now I apply the limit, you substitute h equals 0, and you get 8x. So if you noticed, we got a function. But let's go back to the problem. Now, when we know that the derivative of 4x to the power of 2 is 8x, what is then f prime of 3 of this function? So we take 8 times x and we substitute 3. And we get 24, exactly as before, obviously. Example, let's find the derivative of the function x to the power of 2 minus x and use it to find the equation of the tangent line to the curve at x equals -2. So we will start with a setting for the derivative of a function. This is limit h approaches 0 of fx plus h minus fx over h. So the more difficult part is f of x plus h. I'm just copying the function and I'm replacing all the yellow cubes of x by x plus h. Don't also forget to have brackets or parentheses around the function f of x. The reason is that if you look at the definition of the derivative as a limit, you have f of x plus h minus the function. So make sure you really take minus all the function. So now we're just going to do algebra. We're going to expand the x plus h to the power of 2. And now we would like to get rid of all the brackets in the parentheses by distributing all those negatives. And we get that. And now we're going to start canceling like terms. So those 2 are cancelled. And these 2 are. And this is what left over. And I already distributing the h here, because now I know I'm going also to cancel the h's here. And I get that. Now I can go and substitute h equals 0 for the h. And I get 2x minus 1. So So we get that the derivative of x to the power of 2 minus x is 2x minus 1. Now we can continue. We would like to find the tangent line to the curve at y equals fx at x equals negative 2. So when we have the derivative, we can find the derivative where x equals negative 2 by substituting x equals negative 2 into the derivative. So we take 2x minus 1 and we substitute negative 2 and we get negative 5. So for the equation of the tangent line, I need the slope of the tangent line, which is negative 5, and also I need a point. The point is a point on the graph of a function. So when x equals negative 2, y equals f of negative 2. F of negative 2 is negative 2 to the power of 2 minus 2, and we get 6. So the point is negative 2 and 6. Now I can combine this, and I use the slope point equation, and I get that this is the equation of the line. If you want, you can simplify this a little bit more, and we get that. So we can finish up the problem by stating the solution. The equation of the tangent line to the curve of fx equals x to the power of 2 minus x at x equals negative 2 is y equals negative 5x minus 4.